Hello and welcome to Lecture 15 for the graduate course ECE 254B, Parallel Processing. This lecture deals with chapters 15 and 16 in the textbook, where chapter 15 covers a number of architectures which are either variants of or derived from the hypercube, which we discussed in the previous two chapters. And in chapter 16, we cover a number of miscellaneous parallel architectures, uh, just to give you a sample of what else is available. In other words, what we will see in chapter 16 is uh, sort of the tip of a huge iceberg, so that we are exposed to uh, uh, the large variety of networks that exist, so that we are aware that such networks exist. And if we need to use a network for a parallel computer, we know where to look for uh, all the options that are available. Okay, so let's start with chapter 15, other hypercubic. So hypercubic is basically a general name given to the class of architectures that are derivatives of or inspired by hypercube. Okay, so this is just a small toy example to get us started. Uh, on the left side of this slide, you see a three-dimensional 8-node hypercube with nodes numbered. And as you remember from the previous chapters, the links are characterized as belonging to various dimensions. So in this diagram, dimension 0 links are the horizontal ones, 0 connected to 1, 2 connected to 3, 4 to 5, and 6 to 7. And the node ID distance along dimension 0 is 1. Okay, 0 to 1, 2 to 3, and so on. Dimension 2 are the vertical links in this diagram, 0 to 2, 1 to 3, 5 to 7. As you see, the distance between the node indices are 2. In other words, in binary, the indices differ in the second bit from the right. And finally, the third dimension, 0 connected to 4, 1 to 5, the distance between the indices is 4, or in binary representation, the third bit from the right is different. So here I take this 4 cycle, a cycle of length 4 of 4 nodes, and twist it by changing the connections as shown on the right side of the slide. So this is known as a twisted 3-cube. Why would I do this? Well, it turns out that the diameter of the original hypercube is 3, as we know, three-dimensional hypercube has diameter 3. This network has diameter 2. So by making this small change, we have reduced the diameter from 3 to 2, and therefore potentially have speeded up the worst case latency of message transmission. Okay, so that's a highly simplified view, because by doing this twisting, what I've done, I've sort of destroyed the symmetry, the nice symmetry that existed in the original hypercube. And the load may no longer be distributed evenly among these links as I transmit between different nodes in this twisted hypercube. As I said, this is just a toy example to show you that we can do stuff in order to improve some figure of merit of the network. In this case, the diameter was improved, although it's not clear that this is a worthwhile change. So more generally, in a q-dimensional hypercube, we still take a cycle of length 4, basically one node, two of its neighbors, and the shared neighbor of those two neighbors. Okay, every hypercube will have many such 4 cycles consisting of a node, its dimension I and dimension j neighbors. Okay, and so these will differ from the ID of these nodes, differ from the ID of this one in bits I and j, and this one differs in both bits I and j, so it's a neighbor, a shared neighbor of those two nodes. And I can do this. Instead of these connections, I connect, instead of 1 connected to 3, connected to 7, and 5 to 7 changes to 5 to 3. So this is known as twisted hypercube. Another change that I can make, and this one a little bit better in the sense that it maintains the symmetry of the hypercube. So I take again a 3-dimensional hypercube, but I can do this for any number of dimensions, and provide one additional link for each node by connecting each node to its diametrically opposite node. So 0 will be connected to 7, 4 to 3, 2 to 5, and 1 to 6. So I'm going to add 4 links, 4 new links to this hypercube. Of course, by adding these links, I'm increasing the node degree from 3 to 4. So there is some cost increase, both in terms of the complexity of each node. It now has 4 channels instead of 3, or more generally, q plus 1 instead of q for the original q-dimensional hypercube. So what does this addition buy me? It turns out that this addition cuts the diameter of the hypercube to roughly 1/2. Not quite 1/2 in all cases, but very close to 1/2. Why is that? Well, the reason that it cuts the diameter to 1/2 is that if I take a node from which I want to send a message to another node, if the Hamming distance between the source node and the destination node is less than half of q, then I can send a message normally through the regular connections of the hypercube. If the distance from the source node to the destination node is more than half of q, in other words, the Hamming distance is fairly large, then I can send first from the source node to the diametrically opposite node, and then that diametrically opposite node will be closer to the destination than the original node, because basically in going from this node to its diametrically opposite node, I'm flipping all the bits in the node ID. So 4 is 100, 3 is 011. Okay, it's the basically bitwise complement. And because the distance from the source to the destination was relatively large, when I flip this new node will have a smaller distance to the destination. Okay, so this is known as folded hypercube. It cuts the diameter to roughly half. So in this case, the diameter goes from 3 to 2. Okay. If I had the 4-dimensional hypercube, then the diameter would be cut exactly in half. We'll go from 4 to 2. So for even dimensional hypercubes, the diameter is cut in half. For odd dimensional hypercubes, the diameter is cut to almost half, a little bit more than half. Okay, so is this a worthwhile trade-off? As I said, uh, the cost of each node increases. Also, because I have more wires, if I try to lay this out on a VLSI chip, it will occupy more area to accommodate the original links plus these new links. Okay, so one thing I gain is the shorter diameter. Another thing that I gain is a wider bisection. The bisection width increases. There are more wires that I need to cut to bisect the architecture. So that's one advantage. Another interesting advantage is that now my hypercube, the folded hypercube, can be viewed as a fault-tolerant regular hypercube. So let's imagine that all dimension 0 links, or at least one of them, has failed. So I've removed dimension 0 links here, assuming that one or more of them have failed. So communication along dimension 0 is no longer feasible because one or more of those links are missing. Okay? Well, I can sort of twist this hypercube back into this shape by rearranging the location of the nodes. And now that's, so basically those diametral links can be viewed as an extra dimension. So now those links shown in boldface here take the place of dimension 0 links that have been removed because one or more of them was not available, malfunctioning. Okay, so this folded hypercube can lose links along one of its dimensions, one or more links along one of its dimensions, and still be able to act as an ordinary hypercube. So it has become fault tolerant. Of course, I have to renumber the nodes in order to take advantage of this additional dimension spare. You can view this as a spare dimension that can replace the other dimensions when one of the dimensions is not available. Okay. The next category is generalized hypercubes. Excuse me. Remember I said that a Q cube, a Q-dimensional hypercube, is the qth power of K2, the two-node complete graph. So if you take the two-node complete graph, raise it to the power Q, you get the Q-dimensional hypercube. That's how one way to construct it. Well, this suggests an interesting generalization. What if I use K3 or K4 as sort of the basis or the initial network? So here is K4, a four-node complete graph where every node is connected to every other node. If I raise this to the power Q, in other words, multiply by itself Q times, I get a network that is known as generalized hypercube. So it shares with the hypercube the structure that it's the qth power of some basis network. But that basis network, instead of being the two-node complete graph, is the four-node complete graph or the three-node complete graph. Okay, so we call this, so this is binary hypercube or radix 2 hypercube. You can view this as radix 4 hypercube. Node numbers are now radix 4 numbers. So for example, 0, 1, 2, 3 along this dimension, and 0, 1, 2, 3 along another dimension, and so on. So node IDs will be radix 4 numbers. And then two nodes will be connected to each other if their corresponding indices as radix 4 numbers differ in one digit. So here, connection was between two nodes whose IDs differed in 1 bit, and here connections exist between nodes whose IDs differ in 1 digit of the radix 4 ID. Okay, here's another way to generalize the hypercube. Remember, in the recursive construction of hypercube, I said that the Q cube is basically 2Q minus 1 cubes, where the corresponding nodes are connected to each other. So we started with the 2-node hypercube, or one-dimensional, then took 2 copies of that and connected the corresponding nodes to get the 2-dimensional, or 4-node hypercube. Then we got 2 copies of the 4-node hypercube to form an 8-node, or 3-dimensional hypercube. Okay, you can do the same thing with other starting networks rather than just the 2-node graph, K2. Here, I'm starting with K3, 3-node. Okay, so this is the basis network. Here is a second copy. Now, instead of insisting that node 0 of this graph connected to node 0, as it is here, node 1 to node 1, node 2 to node 2, I just insist that there's a one-to-one connection or mapping between the nodes. So in this case, node 0 is connected to 0. Node 1 is connected to 2 in this graph. Node 2 is connected to 1. So this is called a one-to-one or bijective mapping. So I start with a 3-node graph, do this bijective mapping, and end up with a 6-node graph. Take 2 such 6-node graphs and do another bijective mapping. Again, no need to connect nodes with the same ID or same number to each other. Any one-to-one mapping is acceptable. And then finally, I take this 12-node graph. Here's another copy of that 12-node graph, and do a one-to-one or bijective mapping to get a 24-node. So in such graphs, the number of nodes does not have to be a power of 2. In this case, you see, for example, I have a 24-node or a 12-node network. And by judiciously selecting these bijective mappings, I can reduce the diameter. So in the case of hypercube, the diameter would be Q if I repeated this Q times. So let's say I do start with 2 nodes, then go to 4 nodes, but I don't insist that the same node numbers be connected to each other. If I do this judiciously, these connections, the diameter actually can be less than Q. Okay? However, again, there's a trade-off here. If I have this, what appears to be a more or less random connection, then developing algorithms might not be as easy as it was in the case of the hypercube, because there isn't a regularity or regular recursive structure. There is a recursive structure, but the bijective mapping changes at each level to some arbitrary bijective mapping. Okay, again, this is more of theoretical interest. The nice thing is that I can reduce the diameter of such a network by selecting the bijective mappings that I use. Okay, butterfly networks we studied in the section on shared memory computers because butterflies can be viewed as processor to memory or processor to processor interconnection networks. So I'm going to skip this section, fat trees we discussed, multi-stage interconnection networks, Benesch networks, and so on. So this is another network that is inspired by the hypercube. So here I have what's looks superficially like a three-dimensional hypercube in terms of the nodes, labeling, and arrangement. However, there are additional links besides the hypercube links. So the hypercube links are the ones shown uh, using heavy lines, dark lines, and the other links are extra. So the difference between hypercube and this is that in the hypercube, 0 and 1 are connected to each other, 2 and 3, so this is dimension 0 links, 2 and 3, 4 and 5, 6 and 7. But the difference between node numbers is 1. Okay? 1 is not connected to 2 in ordinary hypercube. However, here we do connect them. So basically the rule here is that any node is connected to any other node whose node ID differs from it by plus or minus 2 to the I. So 0 is connected to 1 because the ID differs by 2 to 0, but only 0 to 1, not 1 to 2. 2 is connected to 3, but 3 is not connected to 4 in the hypercube. Okay, so I add all of those links. So here are my dimension 0 links. Of course, for node 1, there are 2 dimension 0 links. The one that goes to the node with smaller ID and the one that goes to the node with larger ID. Okay, so we can call this 0 and 0 prime or whatever, some other way of naming them. Here are dimension 1 links. Again, the heavy lines are the hypercube links. The thin lines are the ones that we are adding. And finally, these are dimension 2 links. Here I don't add anything because connecting this node to that node basically doesn't add any capability. It's the same connection. So the number of links doesn't quite double because along this last dimension, I don't double the number of links. Or in the other dimensions, I do double the number of links. Okay, the unfolded version of this plus or minus 2DI network looks like butterfly. Again, it's different because it has additional links. So this is the unfolded plus or minus 2DI network. Again, you see all the butterfly links in place here. 0 connected to 1, 1 to 2, but the butterfly does not have these two connections, 1 to 2 and 2 to 1. Okay, so it's a richer network in terms of connectivity than butterfly. Okay, another network that is inspired by the hypercube is the cube connected cycles network. Okay, before discussing the cube connected cycles network, let me show you a general strategy for deriving a new network from an existing network. So let's say I have an existing network in which each node X is connected to 8 neighbors. So this could be the 8-dimensional hypercube or any other network whose node degree is uniformly 8. So each node X has link 0, link 1, link 2. You can call these dimension 0, dimension 1 if you will, but they don't have to be dimension. So each node has link 0, link 1, link 2, all the way to link 7. So node degree in this network is uniformly 8. I've shown just one of the nodes. There may be perhaps hundreds of nodes, thousands of nodes. Every node has 8 neighbors. Okay, node degree is 8. I can change this network in which node degree is 8 by replicating this node X and having 8 copies of it called x0, x1, x7, with each of these inheriting one of those links of the original node. So X had this link L0, L0 would be connected to X0. X had L1, L1 will be connected to the copy X1 of X. So when I do this for every node, the number of nodes is multiplied by 8 in this example. I'll have 8 times as many nodes. So it will be a larger network in terms of the number of nodes. But the node degree will be lower. The node degree will be only 3 because each node has 2 links inside this cycle. This cycle has replaced that one node. So each node has 2 links inside the cycle that replace the node X, and one external link, which is one of the original links of this node. So imagine all the other nodes in the network also replaced by the corresponding cycles, and these connections made between those cycles. So doing this will multiply the number of nodes by 8 in this example, and reduce the node degree to 3. So I've simultaneously increased the network size and reduced cost of each node because each node now has 3 neighbors. Okay, so this is a general strategy to reduce the cost of networks in terms of node degree and also increase its size. So let's apply this strategy to a 3-dimensional hypercube. So here's a 3-dimensional hypercube. Each of its nodes that has 3 neighbors is replaced by a 3 cycle. So now the number of nodes, instead of being 8, is 24, is 3 times as much. In this example, node degree is not reduced because it was 3 originally and it's still 3 in this new network. So only the number of nodes increased by a factor of 3 while keeping the node degree of 3. Okay, so this is known as cube-connected cycles. So there are cycles that are connected to each other as a cube have been connected. So viewing each of these cycles as a node in the hypercube, they are cube-connected in this architecture. Okay, let's take the next larger example. This is the 4-dimensional hypercube. And this node, the yellow node here, is replaced by a 4 cycle. Similarly, every other node will be replaced because the node degree is 4. So we replace each node by a 4 cycle. Now the number of nodes is multiplied by 4. Instead of 16, I have 64 nodes. Node degree is 3 instead of the original 4. Okay? So this is nice. When the number of dimensions in the hypercube is a power of 2, here the number of dimensions, which was 3, is not a power of 2. Here the number of dimensions, which is 4, is a power of 2. So the total number of nodes in the new architecture is also a power of 2. So you can basically contrast this 64-node network to a 6-dimensional hypercube. It has the same number of nodes as a 6-dimensional hypercube. Okay? Whereas its node degree is only 3, a 6-dimensional hypercube has node degree 6. Okay? So it's a cost-saving measure. Of course, performance will be affected by this because you don't have as many links and as many paths between nodes, and the diameter also increases. I'll get to that in a minute. So you're basically trading off some performance for lower cost. So here's another view of the cube-connected cycle. You see on the right, I've redrawn that 8. So basically, this is a redrawing of this cube-connected cycles. There are 8 cycles of size 3 that are connected to each other. Here are the 8 cycles of size 3. And these are the connections. Node 0 of this cycle is connected to node 0 of this cycle. These are the dimension 0 links of the hypercube. Node 0 is connected to node 2. Node 1 of this cycle is connected to node 1 of this cycle, which is 2 away. And similarly here. And node 2 of this cycle is connected to node 2 of this cycle. So dimension 0 links, dimension 1 links, dimension 2 links. And notice that this is related to the butterfly network, because essentially what I've done so this is a wrapped butterfly, meaning that the first and last columns have been merged with each other. Okay, so you see in the wrapped butterfly, I also have the 3 cycles. The connections are different, but you can see that 0 is connected through those wraparound links to 1 and 1 to 0. Instead of providing 2 links here, I'll just provide 1 link here, connect these 2 together. Okay, similarly, node 0 to 2, 2 to 0, instead of providing 2 links, I provide just 1 link. So this is sort of a simplified version of a wrapped butterfly network. Remember, wrapped means that first, so if I draw an ordinary butterfly, it will have 4 columns. Here, I've basically merged the first and the last column to turn it into a wrapped butterfly. So the cube-connected cycles network is related. It's not exactly the same as a wrapped butterfly, but it's related to it in terms of architecture. Okay, so once I design a cube-connected cycle such as this one, remember here I've shown only one of the nodes, the yellow one replaced by 4 cycles. I have to do that for every other node in this diagram to get 64 nodes. And this is a 6-dimensional hypercube, which also has 64 nodes. Okay? So how do I emulate? So suppose I have an algorithm that runs on the 6-dimensional hypercube, and I want the algorithm to run here. What do I do? Well, basically, I say this node has, let's call these dimensions 0 for horizontal, 1 for vertical, 2 for diagonal, and 3 for the links that go inward, the red ones. Okay. So if this one wants to communicate with its dimension 2 neighbor, well, it has a connection to it. But if it wants to communicate with its dimension 0 neighbor, it doesn't have a connection. It has just one. It has only the ring connections plus 1 dimension. In this case, it happens to be 2. Okay, this one has dimension 0 link. Okay, this one has dimension 1 link, and this one has dimension 2 link. So if this one wants to communicate with this dimension 0 neighbor, it has to go through an intermediary. It has to go here. This one does have a dimension 0 neighbor, and inside the cycle is the dimension 0 neighbor of that one. Okay, this emulation will be slowed down because what is done in a single communication. Remember here, also I've simplified by not showing all these wraparound links, so there are a lot more links there. And here I've simplified by not showing all the cycles, other cycles, okay? But the idea is simple. Every node has one neighbor to which it can communicate directly. All the other neighbors have to be communicated with through intermediaries. Okay, so that's why the distance is also larger. So going from this node, let's say, to one node in that cycle, I may have to go to a different node in this cycle in order to go let's say from here to here in order to go across this dimension. And in here, I have to go from that node to another node in order to go through this dimension, and then go to another node to go through this dimension, and perhaps one more step in the destination cycle to get to the destination node. So each step, each communication step in this original hypercube will be replaced with multiple steps in this emulating architecture. Okay, so I pay the price in slower communication, lower performance, but I will also have a lower cost. Okay, so here is basically a diagram that explains how communication takes place. Remember we talked about ascend algorithms? Ascend algorithm is when a node communicates. Let's take the descend algorithm. First along dimension q minus 1, then q minus 2, and so on. Okay, so suppose along this descend path, we have already communicated along dimension j minus 1. So this node has communicated along dimension j minus 1 with its dimension j minus 1 neighbor. Okay, after j minus 1, sorry, I have to go back, I guess. Let me see, just 1 minute. Am I doing descend or ascend? Yeah, I'm doing ascend, sorry. So dimension j minus 1 communication has taken place. Then in order to do the dimension j communication, which is what comes next in the ascend algorithm, I transfer the data from this node to this node, and I transfer data from this node to this node, and then I do the dimension j communication between this node and its dimension j neighbor. And I transfer the data to here, and this one also moves, and I do dimension j plus 1 communication. So by one rotation in this cycle, every node will be aligned successively with its different neighbors. Okay, in this case, I've shown dimension j minus 1 neighbor, dimension j neighbor, dimension j plus 1 neighbor. Okay, so as long as communication takes place in the ascent order, then this scheme works. It's just, between communication steps, I have to do this extra work of transferring things from one node to another node. Okay, if I wanted to do descent, then rotation in the cycle would occur in the opposite order. If I want to do normal algorithm, then I would have rotations in various directions. So from j, I go to j minus 1, I go to j. If I want to go back to j minus 1 in the next step, I have to reverse the direction of the rotation. But the next dimension along which I need to communicate is always one hop away in the cycle, and therefore that's why normal algorithms are suitable for this kind of emulation. If the dimensions along which I communicated were just randomly chosen, then I would need multiple rotation steps between the communication steps, and that would be slower. Okay, so this interconnection is known as the shuffle interconnection. And the name shuffle comes from the fact you can visualize these 8 nodes as 8 cards in a deck. You take the first half of the deck, and you take the second half of the deck, and you shuffle them, perfect shuffle. Sometimes this is called the perfect shuffle network. So that this 4 goes between 0 and 2, 5 goes between 2 and 4, and so on. So this is a perfect shuffle connection. And this is an exchange connection. This is sort of like dimension 0 in a butterfly. And this is known as a shuffle exchange network. In other words, connections between nodes in this column and this column consist of shuffle connections, as here. So all the shuffle connections exist in this diagram. Plus shuffle exchange. So shuffle takes me from 0 to 0. Exchange takes me from 0 to 1. So 0 to 1 exists. So this is a shuffle connection. This is a shuffle exchange connection. This is a shuffle connection, 1 to 2. But because 2 is connected to 3, 1 to 3 is a shuffle exchange connection. So this pattern of connections between the two columns is known as shuffle exchange connectivity. Okay, why is this important? So this is a shuffle exchange network. I'll let you study it on your own. Remember that in butterfly network, we changed interconnection between columns to exactly this pattern. So please go back to butterfly and look at the diagram there. In order to make connections between different columns uniform. So that uniform pattern that we saw there is the shuffle exchange connectivity. And of course, this is basically another way of implementing shuffle exchange. We save some of these links. Instead of having a shuffle exchange connection directly, shuffle exchange is implemented in 2 steps. So 0 is connected to 0, that's the shuffle. The exchange 0 to 1 is implemented here. So if I want to do shuffle exchange, I have to do it in 2 steps. Okay, and again, this connectivity is what we had when we designed the FFT network using the butterfly. So this basically says that what we did there, although we didn't call it by this name, was using the shuffle exchange connectivity to implement FFT. Okay. So routing in shuffle exchange networks is pretty simple. So here's a source node with a binary ID. Here's a destination node. We identify the positions in which the two IDs differ, and these caret symbols are the 4 positions in which they differ. Okay, so in the most significant position, I have a 0 here, I have a 1 here. I adjust that one first, basically by doing a shuffle. What the shuffle does, I forgot to mention in the previous slide. Let me go there. So 0, 0, 1 is connected to 0, 1, 0. That's basically a left shift of that. 0, 0, 1 left shifted becomes 0, 1, 0. 2 left shifted becomes 1, 0, 0. 3 left shifted becomes 1, 1, 0. 4 left shifted, so basically I do rotate. Left rotate of 4 becomes 0, 0, 1. This one goes from the other end, so that's the connection. Left rotate 5, 1, 0, 1 becomes 0, 1, 1, and so on. So the connection basically corresponds to left rotating the node ID. Okay, so the neighbor of this one, which so I've rotated it, and this 0, notice, has come here. This 0 eventually will move all the way to the end, and I have to match it to 1. Therefore, I do an exchange here to change that to 1. Okay, then I look at the next bit. So So these two are the same, so I just do shuffle. I rotate, rotate, rotate. Again, here I have a difference between 1 and 0 in the next step. I do a shuffle and an exchange. Okay, so in every step I do a shuffle step to a neighbor whose ID is the shuffle of the current node, and then I do an exchange only if that bit needs to be adjusted to match the other bit, which is different. Okay, so in the worst case, I need 2. If this is a qubit node ID, I need 2 times q steps, because the worst case, I need shuffle and exchange in every step. It's actually a little bit less than 2 times q, because the final steps can be saved. So the diameter of shuffle exchange network is 2q minus 1. And this is a multi-stage shuffle exchange network, which is the same as butterfly network. Okay, so the last thing I'm going to say about networks that are derived from hypercubes are the so-called pruned hypercube. So here I've shown a 3-dimensional hypercube. Dimension 0 links, the horizontal one. Dimension 1 links, the vertical ones. And dimension 2 links, the diagonals or slanted ones. Okay, I keep all the dimension 0 links. Okay, every dimension 0 link is still there. Of dimension 1 links, I remove them in this subcube, but keep them in this subcube. Of dimension 2 links, I remove them in this subcube. I keep them in that subcube. So roughly half of the links are removed. Not quite half, because in one dimension, I keep all the links. All the other dimensions, I remove half of the links. My objective is to make the network simpler, lower cost. And in fact, here you see that node degree was reduced to 2, whereas it was 3 originally. Of course, this is the resulting architecture is a trivial 8-node cycle, but it will be more interesting for higher dimensional hypercube. The diameter increases by 1. Instead of being log 2p, becomes log 2p plus 1. The node degree is cut roughly in half. Instead of log 2p, it's almost log 2p over 2. Bisection width is also reduced. Instead of p over 2, it's p over 4. So this is a downside. 1 unit larger diameter, although 1 unit is not really that bad. And this is a plus. Node degree is reduced. This is also a downside, smaller bisection. Okay, so here is another example. I'm not going to go through it. It's another way of defining an architecture based on node IDs. So X is the ID of a particular node, and I show how that ID is modified to identify the neighbors of that node. Okay, so these are known as Mobius cubes as opposed to hypercubes. And you see here, this one looks like the twisted cube, but it's not really a twisted cube. In this size, it is a twisted cube, but for larger hypercubes, it will be larger cubes, it will be different. Okay, so now let's go into chapter 16 and look into a bunch of other architecture and some general ideas about how to assess an architecture. An architecture is basically the way we are viewing it is a graph, okay? It's a graph with nodes being the vertices of the graph and links being the edges of the graph. So just as we have millions upon millions of different graphs, we can define graphs differently. We can have millions upon millions of different architectures, parallel architectures. Of course, not all of these graphs are useful in terms of having desirable properties, but we don't know ahead of time, what network is good, what is bad. We have to have a way of assessing the goodness, uh, assessing the value of a network. Okay, so here's an example, a partial list showing a bunch of what we call direct networks. Direct networks are the ones in which processor nodes are directly connected to each other, as opposed to indirect networks or multi-stage networks in which nodes are connected through intermediate switches. Okay, we talked about diameter for networks. Another parameter of interest is average distance, or sometimes we call it average internode distance. So look at this 3 by 3 mesh. The diameter we know is 4, pretty easy to determine. The average internode distance requires a little bit more work, okay? Now, when the network is completely symmetric, the work is reduced because all I have to do is to find the average distance from one of the nodes to all other nodes, and that will be the average distance for the entire network, okay? But here, nodes, there are 3 kinds of nodes. There's the central nodes, 4 neighbors. There are the corner nodes. So the corner nodes have symmetry. Okay, it doesn't matter whether I take this corner node or this corner node, the distances are the same with the other nodes. So there are 3 categories of node: the center node, corner node, and the side nodes. Okay, let's take this corner node. The sum of distances from this corner node to the other nodes, okay, the distances are 1 to 2 of the nodes. There are 2 to 3 nodes, to this one, to this one, and to this one. So these 3 nodes are distance 2. These 2 nodes are distance 3, and this single node is distance 4. So the sum of distances from P0 to all other nodes is 18. Similarly, the sum of distances from this side node to all other nodes is easily computed to be 15. And sum of distances from the center node to all other nodes is 12. So to compute the average distance, I have one such node. Okay, so 12 counts only once. I have 4 side nodes. That's why 15 is multiplied by 4. And I have 4 corner nodes. That's why 18 is multiplied by 4. And I divide this either by 9 times 8, because from each node, each of the 9 nodes, I have 8 other nodes to try to reach. So 9 times 8 is basically the number of paths, in which case the average comes to 2. Or I can divide by 9 squared. Basically, I say when I average the distances, I'm interested in distance from P0 to P1, P0 to P2, and so on, but also P0 to P0. That happens to be 0. So instead of dividing by 72, which is 9 times 8, I can divide by 81. So there are 2 ways to divide the average distance. Count these distances of 0 in computing the average distance, or ignore those distances. In fact, this is a better way to do it. It's cleaner. Okay, so in this case, I have 9 nodes. 9 squared is 81. and the average distance comes to 16/9. Either interpretation is correct, but it's cleaner to do it this way. I'll basically show you why. Okay, if this were a torus, then it would be completely node symmetric, and therefore I needed to consider only one node and compute the distances from that node. So this node in the torus is distance 1 from 4 nodes, this one, this one, this one through the wraparound link, and this one, and is distance 2 to 4 nodes, this one, this one, this one, and this one. These 4 nodes are distance 2 away. Okay, so 12 divided by 9, because I have 9 paths, including the path from P0 to P0, the average comes to 4/3, which is a smaller number than 16/9, because those additional links help. Okay, so this is basically the strategy to compute average internode distance, and for symmetric networks, the work is reduced. The amount of work is reduced because you just have to compute distances from one node to all other nodes, and that will be the average distance for the entire network. Okay, so what is the average distance of this 3-node linear array? The average distance of this 3-node linear array is, from this one, I have 1 and 2. So sum of distances is 3. From this one, I have 1 and 2. So sum of the distances for this one is also 3. And for this one, I have 1 and 1. So 8 is the sum of the distances. And I have to divide this by okay, so the average distance in this 3-node linear array is, I have to divide it by 9, sorry, by 9, because there are 9 paths. P0 to P0, P0 to P1, P0 to P2, and then P1 to P0, and so on. So it will be 8/9, okay? 8/9 will be, so another way to compute the average distance in the mesh is say, okay, the average row distance is 8/9, the average column distance is 8/9, therefore the average distance is the sum of those two. And this is the way in which this counting the node itself, the distance of 0, is helpful. Because in going from P0 to P1, I don't do any column movements. I just do row movements. So you can say that the column movement is 0. Okay, that's why you can add things along different. So if this were a 3-dimensional mesh, I could say, okay, the average distance along this row is 8/9. The average distance along column is 8/9. The average distance in the third dimension is also 8/9. So 24/9 would be the average internode distance of this 3-dimensional 3 by 3 by 3 mesh. Okay. Now bisection width is much harder. So average distance, you needed to do some work, but it's not conceptually difficult to compute the average distance. Bisection width, on the other hand, is a very difficult problem. In fact, determining the bisection width of an arbitrary network is an NP-hard problem. And this example shows us why. Okay, here I have a 32-node, what we call chordal ring. It is a ring, So nodes 0, 1, 2, up to 31 are connected as a ring. And then there are chords. So for example, 1 is connected to 12. So 1 plus 11. 0 is connected to 11. 2 is connected to 13. So each node is connected. I is connected to I plus 1, I minus 1, I plus 11, and I minus 11, modulo 32. Okay, so this is a chordal ring. It looks very symmetric. Therefore, one might be tempted to say that that double line that I've drawn bisects the network. And I can't do better than that. In other words, bisect the network by cutting fewer links than what you see there. But in fact, I can do that. It's not very intuitive how, but I can do that. See, the bisection doesn't need to go from one side of the network to the other. It can be quite irregular. For example, it can go from here to here, then go from here to the other side. And in fact, it turns out that there's one such bisection that is much smaller than the one. You can easily count the number of links that I'm cutting in this bisection, but the minimal bisection require cutting fewer links than I've shown here. So here's an example of a network whose bisection width is not as large as it appears. So how do we determine bisection width? There's no general strategy for determining bisection width. So let me show you one that works in some cases. So we can establish an upper bound on the bisection. And if the upper bound is tight, then maybe just as good as knowing the exact bisection. So we typically are satisfied with the lower bound or upper bound for bisection if the exact bisection cannot be determined easily. So here I want to determine the bisection width of this mesh. Okay, here it's easily seen that it's 4. But imagine if this were a much larger network and not a mesh, then it wouldn't be as easy. So I take the complete graph of the same size, so the 9-node complete graph, and embed this into this mesh. Now the complete graph, there's no doubt that the bisection is basically cut it so that there are 4 nodes on one side, 5 nodes on the other side. And because of its symmetry, it doesn't matter which 4 nodes are on one side, which 5 nodes on the other side. And then every of the 4 nodes on one side is connected to every one of the 5 nodes on the other side. So the bisection width is 20, 4 times 5. Okay? So for the complete graph, I easily find the bisection because of its symmetry. Okay? However, here I don't have symmetry. So how do I determine the bisection width? I embed this network into this. So let me go to the next slide where a nicer drawing. This is from the textbook, but since then I've drawn this nicer diagram. So the nodes of the complete graph are 0, 1, 2, 3, 4, 5, 6, 7, 8. And then every node must be connected to every other node. So for example, 0 must be connected to 1. That's this embedding over there. 0 must be connected to, that's this line a little bit further down. This line connects 0 to 2. 0 must be connected to 3. That's this line. 0 must be connected to 4. Let's see, where is that line? It's over here. 0 is connected to 4 through this line. 0 must be connected to 5. It is this line that connects 0 to 5. 0 to 6, that's this line, 0 to 7. So basically each link in the complete graph is mapped onto a path. So 0 to 7 is this one. And finally 0 to 8 is this one. Okay, and similarly for all the other nodes. And in doing this embedding, I try to distribute the load to the different links as evenly as I can. Here I have not succeeded in doing it. I don't know if you can actually do it, but it's pretty close. So there's a minimum of 4 edges of the complete graph mapped to this edge of the mesh, a maximum of 7. Okay, so that maximum is important to me. 7 is the maximum. Now, in order to bisect the complete graph, remember I have to cut 20 of the original links. This means I have to cut 20 of these paths. Cutting one edge of the mesh cuts at most 7 of the paths that I've constructed. So I need to cut at least 3 mesh edges for them to add up to 20. Okay? Because the maximum number of edges of the complete graph mapped to a mesh edge is 7, and I need to cut 20 of the complete graph edges, or 20 of these paths. I need to cut 3 of the mesh edges at least. Okay? So this basically tells me that the bisection width of this 3 by 3 mesh is at least 3. Okay, so this is basically one way to establish a bound on the bisection width when we can't determine the exact bisection. For many networks that have been proposed over the year, bisection width may not be known, but sometimes we have bounds that are pretty close to the actual bisection. For others, particularly symmetric networks, it's easier to determine the bisection width. Okay, now degree diameter relationship. Now, in graph theory, many decades before computers and parallel processing were discussed, graph theorists were interested in this question, an age-old question. What is the best way to interconnect p nodes of degree d to minimize the diameter d of the resulting network? So I'm given p nodes of degree d. So for example, let's say node degree is 4. So each node has 4 ports, and I have 1,000 of these nodes. Okay, how should I interconnect these 1,000 nodes of degree 4 to minimize the diameter of the resulting network? Okay, alternatively, given the desired diameter d, let's say I want to have the diameter no more than 50. And again, I give you degree 4 nodes. Okay, how many of these nodes, what is the maximum number of such nodes that you can interconnect without the diameter exceeding the bound that I gave you, 50? Both of these problems are open problems in general, and people are still investigating them and coming up with partial results. The problems are still unsolved. Okay, so there are 2 bounds known as Moore bounds. One bound is for digraphs or directed graphs, and one bound is for undirected graphs, or just simply graphs. If I have a directed graph, the total number of nodes that I can put into it, if the diameter is bounded by d, is given by this expression. The reason is that this is node x, one node, that's the 1 there. That node has d neighbors because it has d outgoing links. each of those d neighbors have d neighbors in turn, so there are d squared nodes that are distance 2 away, and then d cubed nodes that are distance 3 away. And assuming that there's no repetition, all of these are new nodes. Each layer has different nodes. I just add those up to get the total number of nodes. So this is a bound. In other words, the number of processors cannot exceed 1 plus d squared plus d to the power diameter, which can be simplified to this. Or in reverse order, the diameter in terms of number of nodes and node degree is this: log base d of p times d minus 1. Okay, so roughly speaking, log of p in base d. Okay, so this d minus 1 contributes 1 unit, because log of d minus 1 in base d is a little bit less than 1. And you can ignore these 1 terms as well. So roughly log of p in base d is a lower bound on the diameter. Okay, any network for which equality holds is known as a Moore graph, or Moore digraph in this case. So only ring and the complete graph of size p match these bounds. No other graph matches this bound. In other words, the number of nodes is strictly less than this number, but the diameter is strictly greater than this number. Okay, when you go to undirected graph, then we still start with one node. It has d neighbors, but then each of those has d minus 1 other neighbors, because one of the neighbors is already used here. So the expression is given here. Again, so d minus 2 divided by d, let's take that to be roughly 1. So this is still log of p minus 1 in base d minus 1. So of the same order of magnitude as that. Again, undirected graphs that are Moore graphs are only these: ring with odd size p. So for example, 5-node ring is a Moore graph because its diameter 2 matches this bound. 6-node ring is not. Even size rings are not Moore graphs. Okay, and a few other networks that I won't discuss here. So one particularly interesting Moore graph is what we call the Peterson graph. Okay, Peterson graph. So these are 3 different drawings of the Peterson graph. Okay, so in this drawing, you see there are 10 nodes. Node degree is equal to 3. So if node degree is, so this is undirected. So going here, if the diameter, if the number of nodes is 10, so this is 1, this is 3, this is 3 times 2. So that's 10 already. So diameter 2, so this is distance 1, this is distance 2. Diameter 2, 10 nodes, degree 3 equality holds here. So the Peterson graph is a Moore graph. Okay, there's no degree 3. It has diameter 2, and number of nodes equals to 10. So how good are meshes and hypercubes with respect to this bound that we found, Moore bound? Well, for d equal to 4, which is for mesh and 2D mesh and torus, Moore bound reduces to this, log base 3 of p plus 1 over 2. But for mesh, the diameter is not logarithmic, the square root. Okay, so mesh and torus are far from optimal in this sense. D-dimensional, d cube or d-dimensional hypercube, where d is equal to log 2p, node diameter according to Moore's bound is d over log d. For the hypercube, we have d. So hypercube again is not optimal because its diameter d is larger than the optimal diameter according to Moore bound. Of course, there's no guarantee that we can find a Moore graph, but theoretically, the diameter can be as low as this, whereas the hypercube is d. Okay, so to summarize, for node degree d, Moore's bounds establish the lowest possible diameter d that we can hope to achieve with p nodes, or the largest number p of nodes that we can hope to accommodate for a given diameter d. Usually we are satisfied if we come within a constant factor of the bound. Okay, notice in both these cases above, we did not come within a constant factor. Here, instead of log of p, we had square root of p. Here, instead of d, we have d divided by log d, so this is not a constant. Okay, coming within a constant factor is often considered sufficient to claim that our architecture is efficient in terms of the Moore bound. Okay, other than node degree, diameter, average distance, and so on, layout area and longest wire are also important when we lay out networks on VLSI chips or on printed circuit boards. Now, if a node has bisection B, this is easily proven. The chip area for it will be at least proportional to B squared. Okay, so whereas having a large bisection is good with respect to communication bandwidth between nodes, the same large bisection will also basically constrains us because we have to use more area on the chip to lay out such a network. A 2D mesh can be laid out in order P area. In other words, the area of a mesh is linearly proportional to the number of processors. Basically, we don't waste a lot of area for interconnects between the nodes because all the wires are short between neighboring nodes. On the other hand, because the hypercube has a bisection P over 2, order P, and its area, according to that theorem, must be at least proportional to P squared. So a large hypercube will require a lot of area because it will have a lot of wires. Not only that, but also these wires tend to grow. As the hypercube size grows, the area grows according to the square of P, and the length of the wires also grows according to P divided by log P square root of P divided by log. So not only we have more wires, more area, the length of the wires also grows. This is the sense in which hypercube is not scalable because as you grow its size, the area penalty is large, and wire length also grows, therefore slowing down communication between nodes. Okay, one measure of network cost effectiveness that we talked about before is the degree diameter product. So remember, the degree is basically a rough measure of the node complexity and therefore node cost. Not quite. The more ports a node has, the more costly it becomes. And the diameter is basically a measure of communication latency or communication cost, if you will. So we want to minimize this product. In other words, minimize the cost of the node, at the same time minimize the communication latency. So it may seem a good idea to minimize this product. Okay, that product is ordered square root of p for meshes, is ordered log p for binary tree, log p for pyramid, log squared p for hypercube. Okay, so even though it seems that the binary tree has a small degree diameter, so the degree is constant for a binary tree, and the diameter is logarithmic. Okay, remember that binary tree had a lot of other drawbacks, like it wasn't very robust, and also congestion can occur at the root. So, this is not really the sole measure of the merit of a particular interconnection network. Okay, so let me define, I won't even bother to define the pancake network. It's very similar to star. So what is the star network? The star network has nodes whose labels are the permutations of q digits. So the q digits here are 1, 2, 3, 4, so q is equal to 4. And all the permutations of 1, 2, 3, 4, 4, 2, 3, 1, 2, 4, 3, 1 are node labels. Okay? So basically there will be q factorial nodes because there are q factorial permutations. So 4 factorial is 24, and there are exactly 24 nodes in this graph. So what is the connectivity rule? The connectivity rule is like this. Two nodes are connected if the label of one can be derived from the other one by switching the position of the first symbol and one of the other symbols. Okay, so if I switch the positions on 1 and 2, I get 2, 1, 3, 4. That's one neighbor of that node. If I switch the positions of 1 and 3, I get 3, 2, 1, 4. That's another neighbor. If I switch the positions of 1 and 4, I get 4, 2, 3, 1. That's the third neighbor. Okay, so the neighbor of a node is another node whose label can be obtained from the original node by switching the positions of the first symbol and one of the other symbols. So because there are 3 such switching possible, 1 and 2, 1 and 3, 1 and 4, there will be 3 neighbors to each node. And we call these dimension 2, dimension 3, and dimension 4 links. There's no dimension 1, so that's for convenience. If you switch the first one with the second one, you call that dimension 2 link. So let's take another example. So 4 and 2 switched becomes 2, 4, 1, 3. So where is 2, 4, 1, 3 is this? So this is a dimension 2 link. Okay, if you switch 4 and 1, you get 1, 2, 4, 3. That's the dimension 3 link. I could have called them dimensions 1, 2, and 3, but 2, 3, and 4 is easier to remember because depending on which symbol you switch for the first one. And finally, switch 4 and 3, you get 3, 2, 1, 4. And that's this node. So that's the dimension 4 link. Okay, so why have we bothered to, as I said, you can define millions upon millions of interconnection networks by thinking up different connectivity rules, different labeling schemes for the nodes, and so on. So why is this good? It turns out that this has diameter q minus 1, whereas it has q factorial nodes. Remember, a hypercube had diameter q, 2 to the q nodes. Well, q factorial is a larger number than 2 to the q. Okay? So this one has roughly the same diameter as the hypercube, but a larger number of nodes. In fact, you can easily prove that both the diameter and node degree of this architecture in terms of the number of nodes is order log p divided by log p. Remember that for the hypercube, both of these, degree and diameter, were order log p. So this one is order log p divided by log p. So it has an advantage in terms of smaller diameter by this factor. Okay? However, everything else for this network is more difficult. So imagine trying to develop an algorithm. So this is basically the 4-star. Okay? The 4-star consists of 4 3-stars. So 3 stars are these hexagons that you see, or 3-dimensional stars. And then each 3-star is basically 3 2-stars. Okay, so it has some recursive structure, but that recursive structure is not very convenient to use for developing recursive algorithm, because in hypercube, each recursion size of the cube was divided by 2, so you could divide the problem into 2 equal parts and then assign them to subcubes. Here is not as convenient. So basically don't do much, can't do much in terms of developing algorithms. But theoretically it's interesting because you have achieved a diameter that is lower than the hypercube. Okay. Just as we define the cube-connected cycles, we can define star-connected cycles. In fact, for any network X, we can have X-connected cycles. So we have cube-connected cycle. Here we have star-connected cycles. We can define other networks like mesh-connected cycles, torus-connected cycles. So here I've taken a 4-star, 4-dimensional star, replaced each of its nodes with a 3, because it had node degree 3, with a ring of size 3. Therefore, I've multiplied the number of nodes by 3 in the resulting network, while keeping the node degree still at 3. Again, the diameter increases, but our hope is that this is a cost-effective alternative to the regular star. Well, regular star was, we had problems to begin with developing algorithms. So algorithms for this star-connected cycles will be even more difficult to develop. So again, it's just a curiosity. But this general structure, remembering it is worthwhile. So X-connected cycles, when you take a network X, where X can be cube, star, or any other network, and replace each of its nodes with a cycle equal in size to the node degree of the original network. So pancake, I said I'm going to skip Cayley networks and show you some other examples. This is what is known as a hierarchical ring. It has been used in limited number of systems. So this is a 2-level ring network. So there are the clusters, level 1 rings, which are these ovals that you see here. One of them is shown in full. The other ones, just one representative node is shown. And there's a second level ring that connects one node of each of these rings to each other. So in going from a node here to a node here, I first have to take a few steps in the local ring of the source node, then a few steps in the second level ring, then a few steps in the destination ring. So distances tend to be larger, but this is a very cost-effective network because the node degree is 4 at most for this one. All the other ones have. If I had this second level ring for every one of those, this essentially would become a torus. So you can view this as a poor man's torus. Okay, it's a torus in which I've removed all those other second level rings, kept only one of them in order to reduce the cost of the network. So we can design, these are known as hierarchical ring networks. I can do to more than 2 levels. Chordal ring networks, we have already seen an example of this, is when, so this is a ring, unidirectional ring network. This is a unidirectional chordal ring network where I've added a chord to each node. So node I is connected to I plus 1 along the ring, and I plus some other number, in this case I plus 3, which is the chord. So each node has in degree 2 and out degree 2. Okay, and the other example. So more generally, each node V has ring links which connects it to V plus 1 and V minus 1. Those are the ring links, plus skip links or chord rings that connect it to V plus S1, V plus S2, all the way to V plus Sk minus 1, depending on how many of these chords. Here I had just one chord, but I can have more than one chord. Okay, so chordal rings can be compared to torus networks. In some ways they're similar. So here is an 8-node chordal ring drawn to resemble a torus. Okay, here's a 9-node chordal ring. So the ring is 0, 1, 2, 3, 4, 5, 6, 7, 8, back to 0. That's the ring part. And then the chords go from 0 to 3, 1 to 4, 2 to 5, 3 to 6, 4 to 7, so it's plus 3, 5 to 8, and then 6 to 6 plus 3 is 9. Just 1 minute. Yeah, 6 plus 3 is 9, modulo 9 is 0, so that's connection. So you see that this has a lot of the connections of a torus, including these wraparound links, except that the row wraparounds, instead of going to the same row, go to the next row. So 2, instead of being connected to 0, as in torus, is connected to 3. 5, instead of being connected to 3, is connected to 6, and so on. So it has some similarity to torus. Okay, and there's also the class of perfect difference networks. It's something that we invented at UCSB, and we published it in 2 parts in IEEE Transaction and Parallel and Distributed System. So I just want to give you an idea of how many different ways you can design an interconnection network so that you're aware of the huge space of possibilities. I'm going to skip periodically regular. Again, that's something that we invented at UCSB. Okay, we can design composite or hybrid networks. And basically, you can take 2 architectures and combine them in some way. So composition can be done by the product operation that we have seen before. So you can take 2 networks, in this case 2 very simple networks, and multiply them to get another network. So that's a composite network derived from the 2 simpler networks. Okay, so let me skip this one too. So we have already seen a couple of examples of multi-level networks. So for example, cube connected cycles can be viewed as a two-level network. At one level, we have, at the cluster level, we have the cycles, and at the basically macro level, large level, we have the cube. This is another example, mesh of meshes. So basically the name of such networks will be excess of y's. So here we have cube of cycles, or another way of saying it is cube connected cycle. But this doesn't have to be a cycle, it can be another. I can use a mesh. So take a node, each node of the hypercube, and replace it with a mesh. Okay. Of course, the hypercube must be larger for this to make sense. For example, if this were a 9-dimensional hypercube, I could put a 3 by 3 mesh to replace each node. So that would be a cube of meshes. So here's mesh of meshes. So I have these small 3 by 3 meshes, 9 of them, and I've connected those as a 3 by 3 mesh. So what is the difference between this and a 9 by 9 mesh? It has fewer connections between these clusters. So in this region, it's identical to the 9 by 9 mesh. In this region, it's identical. Connection between these two regions is missing, these two links. So this is potentially good when the bulk of communications are local. So you have a lot of communications within clusters, and you have occasional communication between different clusters. So having fewer connections is not a major drawback. Also, this will be more packageable. In other words, if you put this on one chip, you put this on one chip and so on, so 9 chips, then those chips will have fewer connections between them than if this were a 9 by 9 mesh that was decomposed into 3 by 3 meshes. Then you would have these additional links too. Okay, the final example that I show you is the swapped connectivity. Again, this is something that we worked on at UCSB for many years. So it's also an example of a hierarchical network. So let's say I take 4 clusters of size 4. Okay, so each of the clusters is a ring, or you can call it a 2 by 2 mesh. Then label each node within the cluster. Okay, so node 0, node 1, node 2, node 3 within this cluster. And this is cluster 0, so the second digit there is the cluster number. So node 0 of cluster 0, node 1 of cluster 0, node 2 of cluster 0, and node 3 of. Similarly, this is cluster 1, this is cluster 2, and this is cluster 3. Then inter-cluster connectivity is governed by this rule. If you have ij, node I of cluster j, it will be connected to node j of cluster I. So that's where the name swap comes from. So the cluster number and node number are swapped to find the neighbor of this one. So each node has basically intra-cluster links within the cluster according to some connectivity for that cluster. And then inter-cluster links are governed by this. 1, 0 is connected to 0, 1, 2, 1 to 1, 2, 3, 2 to 2, 3. So these are known as swapped networks. And they have some very interesting properties, and we have published a number of papers dealing with those properties. In particular, in IEEE transactions on parallel and distributed systems, we proved that swap networks are maximally fault tolerant. So that's a very good property to have. Okay, I'm gonna skip the biswapped network. It's a derivative of swap networks. Data center networks. Much of what we have in current data centers are variants of fat trees. So this is an example of a data center network. These are the servers at the leaves of this fat tree. Then there are various switches, an aggregation node, and then the core nodes at the highest level. So you see that this is tree structured, except that instead of having one root, you have two roots. So this is sort of an implementation of the fat tree concept. Okay, and this section I'm going to skip because we already talked about multi-stage interconnection networks in connection with shared memory, implementation of shared memory. All right, so basically this is it. And there are also networks that are known as small word networks. They don't have application in parallel processing, except that we do want to emulate some properties of small word networks, if we can, in parallel computer interconnection networks. So one property of small word network is that nodes tend to be clustered, with nodes in various clusters heavily connected to each other. And then clusters also connected to each other through some nodes that have a lot of links. And this makes the distance between nodes fairly small. So for example, this is the LinkedIn, a small portion of the LinkedIn connection, where people in one institution or maybe in one area of specialty are heavily linked to each other. They're connected on LinkedIn. Some famous people or highly productive researchers may be connected to people in different disciplines or different institutions. And this is what makes the distance between nodes rather small. You may have heard of the notion of 6 degrees of separation, which says basically everybody is linked to everybody else at most through 6 links. So that property of these small world networks is good if we can duplicate it. But of course, we don't want to have a random network such as this one, because it would be extremely hard to develop algorithms for it. But if we can have a deterministic network that also has short internode distances, that would be a good candidate for parallel processing. All right, so the next lecture, lecture number 16, will be the last one for the course. Until then, stay safe, and I'll see you in lecture 16. Bye.